Hi, welcome to Statistics Online. I'm Naomi Lowe and this is Lecture 3, Part 2. In Lecture 3, Part 1, we covered z-scores. We talked about calculating z-scores from a raw score and a raw score from a z-score, and I introduced you to the normal curve. Now we are going to look at how z-scores relate to the normal curve, how you can use the normal curve along with the z-score to estimate the percentage of people who fall below and above certain scores. And then we will move on to talk a little bit about samples and populations, which I introduced slightly in the first lecture. And then we will talk a bit about probability. Okay, so first let's look at the normal curve. This normal curve should be familiar to you. You should have memorized the different percentages that fall within 1 and 2 standard deviations and beyond. So if we know a z-score, remember our z-scores for those emotional intelligence tests that these candidates had taken applying for a job. If we know their z-score, it can tell us something about how they fall in regards to everyone else who would take these same tests. So here we know that Joe's z-score was -2. That tells us that only 2% of people would fall below Joe. Okay, so that's pretty low. Poor Joe. We also know that about 98% of people out there in the world, not just with our little sample, would score above Joe's score. So we'd have 98% above him and 2% scoring below him. Elizabeth's z-score of -1. We know that if you add 14 plus 2, we know about 16% of people score below her. Not quite as bad as Joe. And we also know that Mary's +2, she is high up there. So she is up here, only about 2% of people are going to score higher than her. So even if they weren't just comparing, if they had one candidate come in and take the test, you could get their EQ test, and without comparing to other candidates, you at least know, okay, they're way up here. Only 2% of people out there in the population are going to score above this. And they might go, that's good enough, we're going to hire this person. Otherwise, they might not, the first 2 candidates might be down here in the low range and they just compare their 2 scores and go, okay, we'll pick the best of them. But maybe they should hold out. If they know that 98% of people score higher than them in general, they should hold out for better candidates to come in until they get someone up in the range that is acceptable. Okay. So suppose I told you that my EQ was my EQ z-score, not my actual score, my z-score was 0.67. Okay, what would that tell you? You know a z-score means that tells you how many standard deviations away from the mean my score is. It's positive, so you know my score is above the mean. And it's not quite 1 standard deviation above the mean, it's 0.67 standard deviations above the mean. So now suppose I want to know what percentage of people score above me and what percentage of people score below me. 0.67 doesn't fall neatly on one of these 0, 1, or 2 marks. So 0.67 is my z-score. How do we figure that out? Well, you're lucky that someone actually made a table. These represent the area under the curve. The entire area is 100% or 1, or if you take 1 times 100 equals 100%. So this total area, someone took little tiny increments and calculated what percent falls within this little tiny portion, or 0.01 z-score, 0.02 z-score. So they took all these little z-scores and found out the percentages on either side of them, and they created this table. We call this z-table, or the standard normal curve table. So let's take a look at the z-table. And you have this, you can find this in the back of your book in the appendix, and it looks something like this, although it's a lot longer. Here, I'll go ahead and show you. In the book, it looks like this. This is your appendix, and that's our z-table. And then I just took a little piece out of it for us to look at so that I can explain how this z-table works. So once you know a z-score, you can go to the z-table and find the area to the sides of that z-score. So here's my z-score of 0.67. Now it'll start at 0, and if you look at this table and how it works, it gives you the percentage from the mean to your score, and then what remains in the tail. So it is really helpful if you draw this out. So if I draw the normal curve, because remember this table is talking about the normal curve, and I put a z-score of 0 right here, what would you expect the area from the mean to that score to be? Well, it is exactly the same as the mean, so of course the area from the mean to that score is 0. Now if you look at the percent in the tail of this, we get 50%, which is logical because 0 is the mean. It divides 50% in each tail. Okay. Now I cut a little bit out of your z-chart. It goes 0.00, 0.01, continues down in really small increments, but I cut a little out and moved to the 0.6s so that we could see my score. So you would go down to my z-score of 0.67, you follow that over, and it gives you the area or the percentage from the mean. So if we draw this, the mean, which we know is 0, to my z-score, I would draw in 0.67, my z-score is right here. The area in here from the mean to my score is 24.86%. So 24.86% of people would fall within that, and then it gives me the area in the tail. So beyond my score, 25.14% of scores would fall in that tail. So if I want to know what percent of people would score higher than me in emotional intelligence, I know that it's about 25.14% score higher than my score that's right here. But if I want to know the amount of people that score lower than me, all I know is how many score down to the mean. But on the other side of the mean, if you recall, we have 50% on this entire half. So if you just add 50 plus 24.86, you get 74.86%. So about 74% or 75% of people would score below this EQ score that I got, and about 25% would score above that score. So you see with this table, you can get any z-score and figure out the percentage of people who fall above or below. All right, now this is the z-table that your book uses. There are many other z-tables. In fact, there's one that's really commonly used. You can Google z-table, and it's probably the z-table that you're going to end up finding. So I went ahead and brought one so that we can take a look at this. It's the standard normal curve table, or the z-table. And the way this works, I don't know if you'll be able to see this. It's a little small, but here on this side it says z. Okay? So I'll just make it bigger. It says z. And you just scroll down the list till you find your z-score, just like we did before on the last table. So I go down, it says 0.1, 0.2, 0.3, 0.4. So you move down to 0.6. Okay? This is where it says 0.6. 0.6 is what it says. But the next number is 0.7. Now, if you recall, my score was 0.67. Okay, so we want in between 0.6 and 0.7. So now you move over here where it says 0.00, 0.01. So you just continue to move until you get to the 0.07, which is right here. This 0.07 corresponds with the 0.6 to make 0.67. So you follow this 0.6 over until you get to the column that has the 0.07, and it gives you one number. The number is 0.7486. Now this number, it only gives you one number. It doesn't give you the mean to a number or the area that's in the tail. This is typically how z-tables work, except for the one in the Aaron and Aaron text. This number is the area to the left of your score. Okay, so once again, I suggest you draw this out. If you have this drawn out and you put your score not quite one standard deviation above the mean, it's 0.67, you know that the area to the left of this score is 0.7486. Now, if you multiply that by 100, you get 74.86%. So it's about 75% to the left of that score. You recall the last time we worked this out together, I had 75% below this score, scoring below me on this emotional intelligence test. So this is just another way to work a table that tells you the exact same information. I had a student a couple semesters ago that said the way she remembered that the z-table, the area is to the left, is that she sings that song, to the left, to the left. So you can keep that in mind when you're working with the z-table. Now, if you notice, the z-tables only have positive z-scores. What if I had a negative z-score? Then her song doesn't work out so well. So if you have a negative z-score, this is why it's important to draw this out. If you have a negative z-score, say I had scored negative 0.67, it would be on the other side and the area would just be reversed. But now 75% would be scoring above me. So it's really important to draw out this curve and think about where this score falls and which direction you're moving. Estimate it using what you know about the normal curve before you move on to look at the true exact decimals of the area or the percentage under that curve. So I suggest you always start off estimating using the rules you know about 1, 2 standard deviations away from the mean, and then check it with this. And if they're way off, maybe go back and try to figure out if you went the wrong direction on this curve. If you drew the picture correctly, you should be on the right track. All right, so here are the steps for figuring out the percentage of area above or below a particular raw or z-score. Okay. First, if you're dealing with a raw score, you need to convert the raw score to a z-score. If you already have a z-score, great, you just start at step 2. Then you need to draw the normal curve, just like I did before. You draw the normal curve, and remember the normal curve has a 0 in the center and 1 as a standard deviation. And you need to draw where your z-score falls on that normal curve. Okay, so you make a rough estimate after you've drawn this in. So let's say we draw in my 0.67 on here. We know it's not quite to the positive 1. Now step number 3, make a rough estimate of the area, the shaded area that you're trying to figure out. So if I'm trying to figure out what percentage of people score below me on this 0.67, this would be the area I would want to shade. I'd want to shade in this area below my score. Okay. Now, if you are making this rough estimate, you can go, okay, it's above the mean, so you already know that you have this 50% here scoring below. And then you, in between 0 and 1, do you remember how much information we have? Let's go back to our normal curve chart. You have 34% up to 1. You know it's going to be less than that 34% because I'm not quite up to 1. So you know that it should not be, the area that I end up with should not be any more than 84%. So you know it's under 84%. So that's your rough estimate that you should use. Okay? That's the third step. The fourth step for calculating the percentage above or below a score is to find the exact percentage using the normal curve table or the z table that you find in the back of your textbook or online. Either of those two z tables work. They both have the same information even though they're organized a little bit differently. So that's the next step. You find the exact percentage. Remember to draw it out to figure out what area they're telling you about. You might have to add 50 or subtract 50% depending on the shaded area that you're working with. So on my example, my score is here, 0.67. You go to your z table. Like we did before, it gives you the area to the mean, okay? And then you have to add 50% to that to find the total area below my score or the total percentage below my score. And number 6 step is to check the exact percentage with your estimate, okay? So we already worked through this. We found that the exact percentage was about 75%. So then I go back to my original estimate. My original estimate was that it would be under 84%, but you know it's above 50 because you have 50 over here. And so 75 is between 50 and 84. It looks like you got the correct answer. And that's what you do to calculate the exact percentage below or above a specific score. Okay. All right, so now I'm going to give you a little bit of practice. I want you to practice, pretend you don't see that. Here is an IQ score of 136. Okay? Now, if you know the mean is 100 and the standard deviation is 16, how many people, what percentage of people score above this score? Okay? Suppose your child came home with this IQ score from a test they had to take to get into a GATE program. And you went, wow, okay, I know the average is 100. It looks like they're above average, but wow, how far above average? Are they way above most people or is this typical? Okay. And so you want to figure this out. The first step, if you remember, is convert this to a z-score. So you remember converting it to a z-score, 136, the score minus the mean, 100, divided by 16, and you end up with a z-score of 2.25. Okay, so that's your first step. Convert it to a z-score. Now you need to draw the normal curve and locate where that z-score falls. So you know 0's in the middle, 1, 2, 3, and your z-score of 2.25 is going to fall about here. 2.25 is your z-score. And your question is, what's the percentage of people scoring above this? So remember, after you draw this normal curve, you're going to shade in the area that you want to find the percentage. So you want to find this percentage is your question mark. Okay. So after you've shaded that in, your third step is make a rough estimate of this percentage using what you know from the information from your standard normal curve. So here's the information we have from our standard normal curve. You know that up to 2 standard deviations above, you only have 2% above that. So if we go here and we know that this is 2%, we can make an estimate that there's going to be fewer than 2% falling above this score. Okay, there's less area than there is to this line. So our estimate is under 2%. Okay. Now your next step, after you've made this rough estimate, you're going to find the exact percentage using your z-table. Okay. And you can look up in your z-table this 2.25. So go ahead and look it up. Look up the z. You might have to flip a few pages. Remember, your z-table's in the back of your textbook. You might have to flip through until you get to the higher numbers and look up 2.25. Let's see. And write down what it tells you. It says the mean, percent to mean. So this score to the mean is equivalent to 48.78%. And then it tells you in the tail there's 1.22%. So this tail beyond the score is 1.22%. So I think you just got your answer to your question. You found the exact percentage from the table. Now you have to ask yourself, do you need to add or subtract 50%? Well, your question you're asking about is right here, the shaded area. And you got that number, 1.22, in the tail when you looked in your table. If you were asking a question about who scores below, then you would need to add 50%, but here you don't. So you have to use a little bit of logic while you're working through this. So step number 5, no, you don't need to subtract or add 50%. And number 6, check this estimate to see if it's similar to your original estimate. So 1.22%, is it under 2%? Yes. Looks like you're on the right track. You can now draw the conclusion that 1.22% of people score above your child's IQ score. Wow. So that means that your child's really, really, really smart. Very, very few people are going to score above them on that IQ test. Okay. I suggest you do a couple more of these, practice. The more you do it, the more familiar you will come with it. Don't skip the drawings. That's really crucial to understanding what you're doing and to make sure that you're on the right track. Okay. All right, so now I'm going to show you the steps for figuring out a z-score if you're given a percentage, okay, from a percentage. So these are the steps if you want to, you don't know a score, but you know someone scored in the top 2%, and you want to find out what their score was. So first you want to draw the normal curve, just like before, and shade in the approximate region that you're interested in. Okay, so I'm going to give you this example so that we can actually practice with this as we move along. This example is that Mensa, this is a club that you have to be really intelligent to join. And in fact, I looked up Mensa online, not a part of Mensa, but I looked up Mensa online and I found that they only allow members to join Mensa if their IQ, the standardized IQ test, falls within the top 2%. So if you take an IQ test, you have to fall in the top 2%. Now, the standardized IQ test that they typically use has a mean of 100 and a standard deviation of 16. So knowing that, what score do you have to get to fall in that top 2%? Okay, so now we're kind of working backwards. If you know that your score here falls in the top 2%, okay, we can draw it on the curve. There's only 2% above here. Now you might logically go, ooh, that cuts off the second standard deviation, but I want you to, what if it was 1.5%? So we're gonna go through this as if it wasn't usable with the rules that you've hopefully memorized by now. So first draw it here, and next you need to approximate the area for the percentage. So we already know it's approximately 2% here. Make a rough estimate of the z-score where the shaded area stops. So again, the rough estimate here, we're going to do +2 for this z-score, but say that it was 1.5%. You would make a rough estimate still of 2. Use one of these estimates that you already know. Once you've made this rough estimate of where this stops, not so rough here, you're going to find the exact z-score using the normal curve table. Okay, so we work backwards here. You take your table, your z-table, and you're going to look up the area. You look up the area instead of the z number. Okay, so you're using the information in the middle of this table. Let me pull the, let's see, the original z-score table. So if we have a z-table like this, instead of starting with the z-score, you have to convert back to the z-score. So you know the area you're looking at. So you're going to look at the area you're concerned with. We're concerned with the tail here. So if you're concerned with the tail, you're going to want to look here until you come down to the tail area that gives you 2%. Okay? Once you find this 2% in the tail area, then you go over to find out what z-score corresponds with that 2%. Okay? So go ahead and look in the back of your book at your z-table. Look in the back of the book, go to the area that says 2%, percent in tail, and 2%. It either has 1.97 or 2.02. Sometimes you have to go in between the two or use a rough estimate. Here, let's go with positive z-score of, so it has 1.64 to 1.63. So that's perfect, that works out. Once you have your z-score using the table, then you check that z-score to see if it's similar to the one you estimated, and then you find the raw score. You already know how to do that. We've gone through converting a z-score to a raw score. So you just convert your z-score to the raw score, and that raw score is the score that cuts off 2% in the tail. Okay. Makes sense? Go ahead and calculate it, see if it works out, and see if you can figure out what the top score is to be included in Mensa. All right. So moving on, we need to talk a little bit about samples and populations, which I briefly introduced to you in our first week in this class. Samples are drawn from populations. Populations are groups that we're interested in. And we talked about this when we talked about descriptive versus inferential stats. Inferential stats are dealing with samples. Typically, in statistics, we're interested in a population, a larger group, like this large jar of gumballs. We might want to know how good the gumballs taste. Are they still stale? Okay. But we might not have time to chew every single gumball, or even want to waste all the gum. So instead of doing that, we draw a small sample from this jar of gumballs and we try them out. Okay. That sample, based on what we find, we go, ooh, a stale one, a stale one, a stale one. We're going to guess, we're going to draw conclusions about the larger population. We're going to guess that if the sample is mostly stale, so is the population of interest. So the same thing applies when we're dealing with humans, when we're doing other research. We're typically drawing conclusions about a larger group. One of the reasons we do use samples is because it would take way too much time typically to interview all the people we're interested. If you think of politics, we want to know how people are going to vote beforehand. Of course, it would take way too much time and money to interview or question everyone who would vote. So we draw samples and we draw conclusions about the population based on those samples. So the population is whoever you're interested in, and the sample is group that you actually collect data from. And that data is what you use to then infer or use inferential statistics to draw conclusions about the population. Now, methods of sampling are important to consider because suppose I'm interested in these gumballs, this large jar of gumballs, and so I just take some off the top and throw them into the sample jar. And I'm going to chew up just these gumballs. Could there be something different about the gumballs on the top? Perhaps they got put into the jar later, and so they're not as stale. So I try them all, and I go, oh, this gum's good. We don't have a problem. We conclude that most of the jar of gum is good, okay, not stale. Well, we didn't sample any from the bottom of the jar, so we don't know. It's not a good sampling technique. So a better sampling technique would be to use this random selection. Random selection would mean we shake the jar up, and we randomly draw gumballs from that jar. And that way we get a little bit from the bottom, we get a little from the top, we make sure we didn't just pick out one certain flavor that was our favorite. And with that random sample, it's more likely that the sample looks like the population or that it reflects the population. So the conclusions you draw about this population are going to be better. Now, many times in research, we would like to have a random sample, but it's not always ideal. Especially if you're going into psychology, sociology, the people who are willing to spend their time and answer questions aren't always random. So many times we end up with what we call haphazard selection, where you get the samples where you can. But then you need to be very careful when you draw conclusions about this population from that sample. So everything we do in here, talking about inferential statistics, is going to be based on this assumption that you've taken a random sample from your population, and that way your sample is likely to represent your larger population. Now, we talked a little bit about the symbols that are used to represent samples and populations. They're a little bit different. When we talk about populations, we talk about parameters. These are what we're truly interested in. If we want to know whether men are smarter than women, we want to know whether all men are smart, on average, are smarter than women. Those are parameters that we're interested in. So the statistics about the population are considered parameters. But typically we draw a smaller sample. We might give 1,000 men and 1,000 women an IQ test and compare them. That's what we call sample statistics. So sample statistics are used to estimate population parameters. So when we take data on a sample and we summarize it, then we decide, okay, what does our population look like? What are the parameters of our population? Our symbols are also different. For the mean of a population, we use this mu. And for the mean of a sample, we either use m or a lowercase x bar. Sometimes uppercase x bar is used for the mean of a population. They are both calculated the exact same way. The formulas are the same. The only difference between these two is how we write this up and whether it came from a population or a sample. Okay. Now, the standard deviation, as you know, for a population is the symbol, and for a sample we either use SD or we use a lowercase s. Okay. There is a difference how these are calculated. This one we divide by n, and this one we divide by n minus 1. And the same thing for variance. It's just those symbols squared for the population or for the sample. So when you see these symbols, be aware that you're looking at sample statistics that are being used to estimate population parameters. Okay. Now, I said I would explain why we divide by n minus 1 when we calculate standard deviation. So let me give you a little illustration. If you have a population with IQ scores that look like this, the mean is 100 and they're spread out with on average by 16. Okay? If you were to draw a random sample from this group, okay, from this population that includes everyone, where are you most likely, say you only got a sample of 5 people, where are their scores most likely to be? Well, you can see there are a lot more people with scores here than there are with scores on these ends. So the chances are higher that you end up getting someone from this range. The chances aren't so great that you end up getting someone out on these tails. And so that means that your sample stats, say here's one score, here's another score, here's your third score, here's your fourth score, and here's your fifth score, your sample stats, if you just look at the standard deviation of this, it's going to be underestimate how far these scores are spread out compared to the population that's spread out there. So the sample typically underestimates the variance or the spread of scores, which is why you divide by n minus 1. If you divide a number by a smaller number, it makes it a little bit larger to compensate for that. So when you're calculating the standard deviation, you remember you take the score minus the mean, how far each score is from the mean, you square it, square that score, and then you do that for every single score in your sample and add them up. And then you divide by, you're getting the average of how far those scores are away from the mean. But this average is unbiased. It's what we call an unbiased estimate because we divide by n minus 1 to make this average just a little bit bigger than it would have been if you had calculated it using the population formula. So hopefully that makes sense why we're using n minus 1. You'll also come to know this n minus 1 as degrees of freedom. We'll talk about that. Don't worry about that yet. We'll talk about that as we get further along. So I want to talk a little bit about probability now. Probability is just the expected relative frequency of a particular outcome. So it's the likelihood something would happen, the probability that something would occur. So if I take a coin, okay, and I flip a coin, and I say, what's the probability that I'll flip the coin and end up on heads? Okay. There's an easy way to calculate that mathematical probability. You take the possible successful outcomes. Well, how many successful outcomes do I have? Either you get heads or tails, so there's only one way I can get a heads. And then you take the number of all possible outcomes. I can get either heads or tails, so there's two different possible outcomes. 1 divided by 2, or 0.50. Okay? Now if we change that 0.50 into a percentage by multiplying by 100, there's a 50% probability that I will get a heads when I flip a coin and just one time. Okay? Same thing happens for many other things. You can go, okay, you're having a child. What's the probability you end up with a girl or a boy? It's about 50%. Now sometimes there's this error. People want to go, okay, if I flip the coin 20 times and I'm on my 20th flip and I've gotten heads, they want to go, okay, there's no chance I'm going to get heads on this next one. That's not exactly true. The probability stays the same for each individual case. Same thing's true with having children. People go, oh, I've had 5 boys. The probability of me having, another girl is, or another boy is really slim. Not the case. Still 50-50. It's the number of successful outcomes. And by successful outcomes, we just mean the outcome you're looking for, the outcome that would fit that category. Heads. I could have said tails was successful, and it would be the other way around, still 50%. So this is the probability. Now, probability is going to be crucial to understanding statistics as we move along. So a couple more things about probability is that probabilities range from 0 to 1. All probabilities range from 0 to 1 or 0 to 100%. So I said 0.50 was the probability of flipping a heads when I flip a coin, okay, or 50%. If I have a probability of 0, that means it cannot happen. Okay? I say that there's probability of 0, that's an impossible event. It doesn't typically happen in statistics. A probability of 1 or 100% means that it's an absolute event. It has to occur. Okay. Typically, you get something in between when we're working with statistics that's in between 0 and 1 or 0 and 100%. Now, the symbol we use for probability in statistics is P. Ooh, that reminds me of another stats joke. I won't tell it. You probably can get it from here. So P is the symbol for probability. And in statistics, we ask the question about when we are using sample statistics. Okay, we're using sample statistics, and we go, what's the probability that the population has differences or looks different? And so a lot of times we use this cutoff rate of 0.05. Okay? And let me give you an example that you'll be able to relate to. If I flip a coin, okay, and I say, this coin's fairly weighted. There's 50% chance of being on either side, fairly weighted. Now you might go, okay, and believe me at first, but then I flip it 500 times, and each time I get a heads. you might start to question, really? And go, you know what, something's wrong about your coin. Maybe it's weighted heavier on one side where it always ends up being heads. You're not going to probably believe me. So what's the point, the cutoff point, where you would stop believing that it's a fairly weighted coin? I might flip it 10 times and get heads, and you go, that could happen. Okay? But people start to really be sure of themselves. If I was to flip that coin more than 95 times and continue to be heads, you would say, no way. I don't think that the chances work. I think you're using an unfair coin. And so remember this 0.05 rate, because if you take 95% away from it, that leaves 5% left over. So when we're dealing with sample statistics, which we're going to get into more in the next lecture, this 0.05 is really important, because once we go beyond that 0.05, or the opposite of that, the 0.95 mark, we start to go, something's different here. And it's probably not just chance that you end up flipping the coin and getting heads all those times. Okay, so this is an important number to keep in mind. And we're also going to make connections between probability and the normal distribution when we move on to the next chapter, to the next lecture on hypothesis testing and making decisions about hypotheses, making decisions about a population based on a sample. We're going to use both probability and the normal curve together, what we know from that information, to draw conclusions about populations based on data we have from samples. Okay. So that's all for today. We've covered, so far, we covered the normal curve, we talked about samples and populations, and we talked about probability. So I had fun. Hopefully you got all of this. If not, feel free to ask me questions, and I look forward to seeing you next time.